Right, now we're going to look at section 14.6, which is reactions of ethers. So ethers, they're generally unreactive under basic and mild acidic conditions. This is why they're often used as solvents in organic reactions. Okay, if you remember, they also have low boiling points, so they evaporate easily. So these 2 points, the fact that they're unreactive and that they evaporate easily, make them an ideal solvent. However, if you heat an ether, in concentrated acid, you will cleave the ether into 2 alkyl halides. And get water as the other product. The mechanism involves 2 substitution reactions. So let's look at the mechanism. We'll look at dimethyl ether. The first step is going to be protonation of the oxygen. This was a common theme that we saw last semester. It makes the carbons more electrophilic. The reason, if you recall, that it makes the carbon more electrophilic is because this oxygen does not want to have a positive charge. So it's going to pull the electrons toward it from carbon, so that there's a larger partial positive on the carbon. Now X minus can attack the carbon, and you break the carbon-oxygen bond. Okay, so X minus acts as a nucleophile. And you get an alcohol plus an alkyl halide. A second alkyl halide can then form with the excess acid in the presence of the newly formed alcohol. So the first step of the reaction is very similar to what we saw before. We are going to have protonation of the alcohol. This protonation makes the carbon more electrophilic, can be attacked by the alkyl halide, and then you get your second alkyl halide plus water as your other product. If the R groups of the ether are methyl, primary, or secondary, it's an SN2 type substitution. If the R group is tertiary, it will go by SN1. If you cleave a phenyl ether in the presence of excess acid and heat, the product is a phenol and an alkyl halide plus water. The phenol is not further converted to an alkyl halide because typically you do not have normal substitution or I should say nucleophilic substitution. Add an sp2 carbon. You can use HI and HBr to cleave ethers because I minus and Br minus are good nucleophiles. HCl is less efficient. And HF does not cause cleavage. In the presence of atmospheric oxygen, ethers can undergo autooxidation. It is a slow process that results in the formation of a hydroperoxide. Now, this is a radical mechanism. And I'm not going to go through it. However, you should recognize that old bottles of ether typically contain hydroperoxides. And hydroperoxides are unstable and can decompose violently. So you need to take caution when you're using ether and make sure it's dated and that you are aware if any hydroperoxides are present and that the ether is then purified prior to use.